Hi all, welcome back. Today I would like to talk about three-dimensional regions. Now, if you remember, we talked about box regions for triple integrals in the last video, so now I want to talk about general regions. So how do I integrate over general kind of blobs in space? Call that E maybe, that's our general blob. It's three-dimensional and then we're integrating it over. So you could think about it as a density or something like that we're trying to kind of find the mass of, if you will. Anyways, I would like to look at this today, and it's going to be a bit technical. Well, it's going to be very technical because, as you can see in three-dimensional calculus or three-variable calculus, the problem isn't going to be the calculus that you need to do. We already know that from single variable. The problem is setting up your bounds of integration. That's where the problems are going to come from. So let's get started with some of that. Now, let's say I have a region and I have x and y in some domain D. Let's just say that my z is defined by being between two functions. So if I have a function here, there's my function 1, and I have a function here, there's my function 2. And then my z is straight, so I can integrate all the way up with my z. Then this region here is defined by this, such that z is between u sub 1 and u sub 2 of x and y. Okay, so now to integrate this, we can take the triple integral over a function is equal to the integral over the domains, over the domain for x and y of the integral between u sub 1 and u sub 2 of f of x and y and z dz and then dA. So you're kind of separating that into a double integral and a single integral. Okay? Now we could have another region where x is between a and b, so x is constant, and then y is between two functions of x, and then z is between two functions of x and y. So if you have a region like that, what you do is you set the integral up like this. You set it up between a and b, then between g sub 1 and g sub 2, then between u sub 1 and u sub 2 of f of x, y, and z, dz, dy, dx. And finally, if you have the situation where y is between two constants, x is between two functions of y, and z is between two functions of x and y, then you have the integral between c and d, then the integral between h sub 1 and h sub 2, and then the integral between u sub 1 and u sub 2 of f of x, y, and z, dz, dx, dy. Okay, so now we'll try an example, and this is going to be a fairly technical example. Let's say I want to evaluate the integral over some box or domain or what have you of the square root of x squared plus c squared dv. And that's bounded by y equals x squared plus c squared and y equals 4. Okay, so what's this going to look like? So we have a paraboloid. We have a paraboloid here. It's going to look something like that. So we've got that there. We've got that there. So this is our paraboloid. And then we're cutting it at y equals 4. So there's y equals 4. So we've got kind of like a sheet that's cutting our paraboloid at y equals 4. We get some sort of cross section maybe. There's our cross section. So we're really dealing with this region in here. That's the region we want to deal with inside of there. So what we want to do is we want to put this in terms of z. So if I want to integrate this going up, we can deal with that like that, I suppose. So if y equals x squared plus c squared, then z is going to be this plus or minus the square root of y squared minus x squared. So you have the top and then the bottom, right? So then we can define a region such that we have x, y, and z. X is going to be between negative 2 and 2. Should make sense because here's negative 2 and here's 2, obviously, because if we're at y equals 4, then if we take the square root of that, that's where x is going to be, right? So, and z is at 0 at that point. So that would make sense that we would have negative 2 and 2. Y is going to be between x squared and 4, so x squared down here and 4 up here. And then z is going to be between our two sides, or the two sides of our parabola here, which should also make sense. Now, if I try to integrate this, I get the integral between negative 2 and 2, then between x squared and 4, then between negative square root of y minus x squared, then positive square root of y minus x squared of the square root of x squared plus c squared dz dy dx. Now, this is an integral we don't want to do. This is a very complicated thing to deal with. So what we're going to do is we're going to change our bounds of integration, try to see if we can make things easier. Instead of looking at it from a y-centric approach like this, we're going to look at it from a z-centric approach. So we're going to have we're going to look at the xz axis. So if we look at the xz axis and we cut it at y equals 4, we take the trace at y equals 4, well, what we get is we get a circle. Because if we take the trace of a paraboloid, we get a circle. So if we take the trace at y equals 4, we get this circle with a radius of 2. Okay? So what we will end up getting is we'll deal with y first, and y is going to be between 4 and x squared plus c squared. So it's going to be between our function and our top bound. So we get the integral over the domain, then the integral between x squared plus c squared to 4 of the square root of x squared plus c squared dy dA. Then we can evaluate this integral, but we're still going to have this domain integral, but that's okay. This is our domain here that we're dealing with. So you get the double integral of, if we take antiderivative of this, we get 4 minus x squared minus c squared times the square root of x squared plus c squared once we do the fundamental theorem of calculus, again with respect to a. So now what we're going to do is we're going to transition this into polar coordinates, because again we're dealing with a circle with a radius of 2, and we're dealing with the sum of squares. Of course, we're gonna make the assumption that x equals our cosine of theta, and y and z equals our sine of theta. Okay, because we don't need to worry about r, we're gonna set xz polar coordinates. Okay, so then if we substitute that in, then we have much easier integration bounds. We go from 0 to 2 pi, then from 0 to 2, 4 minus r squared r dr d theta. And we can evaluate that fairly easily. We get 128 pi over 5. Well, that's a kind of a technical example. Again, it's very important that you kind of understand what's going on with our regions. That's the most important part. This stuff, once you get the regions, integrating these and that stuff is very easy. We just need to make sure that we don't arrive at things like this